Now.
Thank you very much. Thank you very much. First of all, congratulations on your foundation day, and thanks a lot for inviting me here. Uh, I'm not in my best condition right now. I'm slightly I met with an accident, so I can have some problem with hearing. So kindly bear with me. But thanks a lot for inviting me here, and it's really nice to deliver a lecture here at Sagar University. I know a lot of I have lots of friends from Sagar University who have reached to very high level, especially from Department of Applied Geology, and probably the it's a privilege. It's a great honor for a student to become the vice chancellor of the university, and that's what that's how your VC is there. So it's I know plenty of them. I mean, who have graduated from Department of Geology and they have reached to very high level in their career. So it's a great department, and I must can congratulate you for on your foundation day. Keep it up. It's a it's a it's a it's an opportunity for the students. It's a privilege for students to be there at this department, to graduate from this department. Thank you very much. What I plan to do here is something which is which could be new to you. I'll try to give you some basic ideas about earthquakes, and I'll talk mostly on intraplate earthquakes. I'll not do. I'll not try to give you too much of research. In this case, I'll try to talk basic. I'll try to tell you what is happening around you. There's a lot of earthquake activity is happening as of now. Okay, there are a lot of earthquakes which are happening around you now, and I'll try to discuss some of them. And so this presentation is going to be very basic. Excuse me, just 1 minute. Somehow I'm not able to go to the next slide. Just 1 second. Let me try to figure it out what is wrong with it. I'll try to share it again. I'll remove the share and I'll try to share it again. Okay, I got it now. Somehow it got stuck. Okay, so the mantra which I have learned in my last few years while interacting with students. I'm audible. I'm fine. My voice is okay.
Yes, sir.
Okay, thank you. So the mantra which I have learned in last few years when I interact with the student is that's the first question which I ask them. Do you know your land? Now, this question could be very basic, and it has a context in the sense that I'm asking you as a geologist, I'm asking you as a scientist, that do you know your land? Do you know what kind of land you have, where you're staying, where you're studying? What is the geology of that area? What is the since I deal with earthquakes, so I really talk. Do you know about the earthquake history in your area? Do you know how earthquakes occur in your area? Do you know what are the processes, geological processes, which lead to occurrence of earthquake in your area? So that's the question which I generally ask. Now, this question could be is again depend upon what subject you're talking. If somebody is a petrologist, then he will when he asks you to know your land, do you know your land? What he means is that do you know the petrology of the rocks in your area? Do you know the structures which are present in your area? So this question is very basic, but and it's at the same time it's very comprehensive, depending upon what is the context in which you have been asked. You will answer this. So that's the basic theme of this article. That do you know your land? So do you know since I'm a seismologist, I'll basically focus on earthquake processes. This area could be new to you because this is not a subject which is taught very extensively in earth science curriculum, whether it is geology or geophysics. But yes, this becomes important when you go for higher studies or when you go for interviews. So that's why it's important to know the earthquake history, the earthquake processes, the geological processes which led to the geomorphology in your area, the structures which are around. So that's with this I'll start. Okay. The arrows are not working, but the mouse works. Okay. So this is so I'll start from here. So this is you see a map here, and all these green dots here are the earthquakes which you see in this is the India map. So this is the Indian subcontinent, and you see a lot of earthquakes here, which is the boundary of India, Pakistan. Then you see a lot of earthquakes here, which we call as Himalayan arc. We see a lot of earthquakes here, which is we call as northeast region, but it's better to call it as Indo-Burmese arc because that's what geology tells us, which extends into Andaman and Nicobar area, Andaman Sumatra area, and this is the region which produced the largest earthquake on Indian subcontinent, which is Sumatra earthquake 9.2. So we start from here. So there are a lot of earthquakes at the plate boundary. So we call them as interplate earthquakes because they occur at the interaction of two plates. I'll not talk much about plate tectonics because I understand that I'm talking to a scientist, so everybody is familiar with plate tectonics. So there are a lot of earthquakes which occur here at the plate boundary, which is the boundary between Indian plate and Eurasian plate here. Here we call as Sunda plate, so there's a lot of earthquakes which occur here. And then, of course, there are earthquakes here, which is again part of Eurasian plate here. But at the same time, we have lots of earthquakes, like here. You see a good belt of earthquakes here, which we call as Narmada zone lineament, or Narmada zone failed rift, or paleo rift, or aborted rift. There are several names for it, but essentially it is a failed rift. So it's a rift which initiated several 100 million years back, but then could not continue, and then it got aborted, it failed. So there's a lot of earthquake activity which occurs here, and the best and the recent example is a 1997 Jabalpur earthquake here, which occurred in Jabalpur area. So we are located somewhere here. Sagar is here. So we are not far from this what we call as Narmada zone failed rift region. So to close to your department, the nearest earthquake producing zone is basically the Narmada zone region or Narmada zone failed rift region. Besides this, we have several other regions like Kutch failed rift here. We also have which has produced two big earthquakes. One was in 2001, which is known as Kutch earthquake. The other one was in 1819, which is known as Allaband or or Kutch earthquake. There are a lot of earthquakes which are occurring here in Delhi region, and there is a feature here which is called as Delhi Aravali fold belt, which is again kind of a paleo structure. It's not very similar to what we see here, the Narmada Zone linear, Narmada Zone field rift, but it's not very different from this structure as well. So so we have a structure which is Delhi Aravali belt here or fold belt here, which probably occurred, probably is there because of interaction of two cratons, which is what we call as Marwar craton on this side and Bundelkhand craton on this side. So this area has undergone a few episodes of stretching, rifting, and then collision in this region to cause this mountain belt here. We also have a failed rift here, which is known as Godavari failed rift. That's a region which has produced an earthquake, a moderate magnitude earthquake in 1969, which is known as Bhadrachalam. Other than this, we also have a small region of a clustered earthquake activity, which is known as Koina region. So there are a lot of earthquakes occur here. By the way, this is what Professor Srivastava was talking about, the Deccan basalt region. So where we have a lot of earthquakes in a very small region known as Koina Vanadi. We still don't understand fully how do these earthquakes occur. We know that these earthquakes are probably triggered by reservoir, but the seismogenesis for the exact cause of occurrence of these earthquakes is still kind of unknown. We also have a few surprises, like there's a region called there was an earthquake here as Latur earthquake. Now you don't see a clear geomorphic expression here, and this earthquake occurred kind of out of blue. I mean, there's hardly any geomorphic expression or a geological structure by which you can correlate this earthquake, but nevertheless this earthquake occurred. These are all typical stable continental earthquake or the plate interior region earthquake. So what I meant here is that we have earthquakes which here occur here on the interaction of two plates, for example, Indian plate and Eurasian plate. So these are called interplate earthquakes. And then we have earthquakes which occur within the continent because of several processes. But they're not interplate earthquakes, they're called as intraplate earthquakes. So what I'm trying to convey in this presentation is I'll talk more on intraplate earthquake, which occur on Indian subcontinent. But to know intraplate earthquake, it's important to know how do the earthquakes occur in interplate region. Fortunately, we have good knowledge of earthquake occurrence in interplate region, but our knowledge of occurrence of intraplate earthquake is very, very limited, and that's the reason because of which our understanding of the processes which involved leading to these earthquakes is very limited. These earthquakes occur as a surprise in several cases. Okay, but since the title is to know your land, probably as a seismologist, to know your land, the starting point could be somewhere here. So there's something called Seismic Zoning Map of India, which has been derived on the basis of tectonic history, geological features, faults in the region, and accordingly, the entire Indian map has been divided into 4 zones, from zones 5 to zone 2, and we are sitting somewhere here. I mean, the Sagar Department of Geology in Sagar University is somewhere here, which could be at the junction of zone 2 and zone 3. So that's zone 3. Zone 2 is now considered as the zone where the probability of occurrence of earthquake occurrence is the least, is the safest zone, And zone 5 are these zones in Himalayan region where the possibility of earthquake occurrence is very high. We define it on the in terms of acceleration. That what is the expected acceleration because of future earthquake in these regions. So the acceleration which can occur in these regions, for example, zone 5 is almost like 0.36% of G, which is acceleration because of gravity. So that's the highest zone, zone 5, which is in the Himalayan region and the Andaman Nicobar region here. That also comes under zone 5. But Sagar department, the Sagar University, it comes at the almost in the zone 2 or at the or in the worst scenario it comes in zone 3. So that's where we lie as per the seismic zone map of India. Before I go into defining the earthquake processes in a region, before I elaborate on Interpolator earthquake, I will like to draw your attention to a typical, like a typical geology field to like a student, that when you go to a load cut, you see a formation like this. You see a lot of on a road cut. You may, if you're lucky, suppose this is a place close to Pithoragarh in Uttarakhand. So on a road cut, if you are lucky, you can see some rock structures where you see a lot of folds. You may also notice a fault here and there. For example, here you see it's a minor fault nevertheless, but nevertheless it's a fault. So now you try to pick up these rocks and try to apply pressure on it and see whether you can fold them or whether you can break them. Now imagine the force which was required to fold these rocks in such a shape to make them look so beautiful. Imagine the force which was required to break these huge strata of rocks to cause a displacement across a fault. That's the power of plate tectonics. That's what plate tectonics does. That's what these plate tectonics processes. I'm talking about. I'll generally focus on plate tectonics, but then of course there are several other geological processes which are involved in causing folds and faults in the rock strata. By the way, these are the faults. By the way, these are the forces. The moment I start approve, then it does not allow me to move. What is the reason? I got a. Sorry, again, let's start. Yeah. NK Gupta. The problem is it was a message which came on my screen to annotate the screen, and I said yes, and now I'm not able to move the slides up and down. What could be the reason?
Kindly continue your presentation, sir.
Yeah, I'm not able to move my slides now because somebody prompted me to annotate the slide, so I did that, and then now I'm not able to move the slide. You and Dr. Ajay Kumar, who is Dr. Ajay Kumar? I need to decline. I need to again share it because this strange request which keeps coming. Dr. Deveshwalia is requesting to.
Yeah, actually, you are not supposed to annotate. Annotate means you stop sharing.
Right.
It's
So,
okay.
so why this prompt is coming to me?
People, they don't know, na, they keep pressing something.
Yeah, I thought that somebody is asking me to approve it, so I did that, and then
No, no,
got freeze now.
not required. It's okay. You can share
So,
again.
so I'll just give me a second. I'll again. I need to unshare it and then share it again.
Yeah, please.
Yeah, you can see now.
Yeah. Yes.
Yeah. Okay. So I'm back. Okay. So that's the force of plate tectonics. I'll mainly focus on plate tectonics. Yes, of course, there are lots of forces, geological processes which involve in building up topography, in building up of these structures. But my main focus will be on plate tectonics here. So if you look at a map of the globe and you see that uh, you see the bathymetry or topography of a region, you clearly see some high topographic region. You under the sea also you see some high bathymetry, and those are the boundaries. Those are the plate boundaries. The boundaries here within the ocean are known as divergent plate margins or divergent plate boundary. That's where the plate is continuously being created. That's where from the push to the plate comes from, and then then you have boundaries which again with the high topography, for example, Himalayan arc here, which extends right into the island arc in Andaman Sumatra region, goes on like this. Uh, Please don't send this request again and again. So then there are these are subduction zones. These are called as convergent plate margins. That's where the two plates they converge, they come together. That's where one plate subducts under them beneath the other plate. So that we call them as a convergent plate margin. Now, if you plot, if you put all these earthquakes on this map, that's what you get. You see that all these plate boundaries, all these high bathymetry region here, the mid-oceanic ridges, or the divergent plate margin here, or the convergent plate margin here, that's where all the earthquakes occurred. So you have all these earthquakes occurring at either at divergent plate margin, which are generally mid-oceanic ridges, or all these earthquakes are occurring at the convergent plate margin, which are subduction zones, or for example, in the case of Himalaya, it's collision zone we call it, because that these are two continents which are colliding. For us, we use the term subduction, but subduction is basically for where you have oceanic subduction. So you have a lot of earthquakes occurring in subduction zone. Of course, the magnitude of earthquake is larger in subduction zone, whereas on the mid-oceanic ridges, the size of earthquakes is generally lower. So that's what plate tectonics says. So the plate tectonics tries to from the divergent plate margin, the new plate is created, and that's what tries to push. And then of course there are a lot of you know it already. There are a lot of process forces which drive plate to move. So all these plates they move in they are continuously moving in different direction. For example, the Indian plate here is moving in the northeast direction and colliding with the Eurasian plate here and causing earthquake in the Himalayan region. So that's the collision zone here. Then we have subduction zone here. Now it is at these convergent plate margins where we have these interplate earthquakes. But then the plate deforms internally also. So there's some internal deformation which takes place within the plate also, and which causes these earthquakes, because it's not absolutely homogeneous plate. There are deep zones. There are several geological. This plate has undergone several geological process of lifting or failed lifting, because of which we have a lot of diversity in geology, a lot of diversity in. We have a lot of weak structures, diversity in faults. We have a lot of which because of which we have earthquakes occurring within the plate also. So that's how it has happened. So Indian plate has moved from it got separated from Africa, started moving towards in the north direction or northeast direction. The movement was fast. At this point of time, it is moving at a rate of about 5 centimeters per year, and which causes earthquakes here in the Himalaya and in the Balvizak right up to Andaman Sumatra. Now, if you try to relate these with the structures which are which are known, you clearly see that there is a clear association of which are already in fact discussed. So you clearly see a lot of earthquakes occurring in the Himalayan region, Himalayan arc. You also see earthquakes which are occurring here in Narmada Zone region. That's where we have a lot of earthquakes. The 1997 earthquake is the closest and the last, the recent most example from Narmada Zone region. So there are a lot of paleo structures because of which earthquakes occur in all these regions. For example, the Delhi Aravalli region as well. Now, this is all about plate tectonics. This is all about the general process, general knowledge about the earthquake occurrence. But despite knowing so much about earthquake occurrence process, despite knowing so much about geology of this region, we didn't know what physical process cause earthquake occurrence in the region. What is that physical process? And this process was of course, plate tectonics gave us a lot of insight into earthquake occurrence process in a region, but we still didn't know what is the physical process which governs the occurrence of earthquake. And the breakthrough came. There was an earthquake in 1906, which is known as San Francisco earthquake, wherein there was a fence which was continuous, and then there was a fault which is known as San Andreas fault now. And this fence was continuous before the earthquake of 1906, but then after the occurrence of 1906 earthquake, this fence got offset. It got offset by 6 to 8 feet. That's when the idea came that, so this earthquake caused an offset in the fence. And we knew that earthquake release strain, earthquake release energy. So that means this energy must have accumulated before the occurrence of the earthquake along the fault, and that gave rise to the famous hypothesis which is known as elastic rebound theory. If you look at another picture here, these are orange orchards, and you can see that that's the San Andreas fault, and you can clearly see the offset here. So the idea here was that the energy which gets accumulated in previous years it's the same energy which gets released during the earthquake. So there's some elastic accumulation of strain before the occurrence of earthquake, and then the same energy is released during the earthquake. So that was this hypothesis or this theory was known as elastic rebound theory. By the way, this came in 1910, and that at that time we didn't know about plate tectonics. The hypothesis of plate tectonics was not formalized, but nevertheless, we started learning how earthquakes occur. Of course, once the plate tectonic hypothesis was formalized, then our understanding increased tremendously about the occurrence of earthquake. I mean, there's an animation here which it shows how these earthquakes occur, how the elastic rebound theory occurs. I'll try to run it if I can. So you see these are the orchards, orange orchards. So there's a fault, San Andreas fault here. It's getting strained, and then suddenly an earthquake occurs, and you see, of course, a lot of orange coming down. So that's what the elastic rebound theory is all about. And it was such a simple hypothesis, simple theory, that energy which gets accumulated before in the previous years is released during the earthquake. Now, where from this energy comes? This energy comes from plate tectonics. So it's the two sides of the fault, or the two plates on either side, since they're moving, since all these plates are moving continuously with respect to each other. So it loads the fault. It is this motion which loads the fault to cause strain. So at the start, when this fence was, or this row of orange trees, which was straight, it gets strained, and then after the occurrence of earthquake, you get an upset. And that was elastic rebound theory. Now, this was why we keep talking about elastic rebound theory, because this is the basic tenet, this is the basic principle on which all our seismic hazard analysis is based upon. So we try to look for regions where the strain is accumulating, because we know that elastic strain, if it gets accumulated in the seismic period, in the period, for example, now, then it's the same energy which will be released in the future. So that's why all our models of seismic hazard are based upon elastic rebound. So if I come back to the plate tectonics, and if I try to combine plate tectonics and elastic rebound theory, so that now we know that then as per plate tectonics, we know that Indian plate is moving towards northeast, and of course interacts with erosion plate here, and then you can clearly see that the motion here is larger and the motion here becomes smaller. So there's a lot of motion which gets accumulated here in the Himalayan arc to cause earthquake here. And it's the same motion, same relative motion between these two plates which causes earthquake. If you look at Himalayan arcs, this map is slightly tilted. So if you look at the Himalayan arc, you see a lot of earthquakes here which are occurring here. The 2015 Gour earthquake is the latest one. You also have earthquakes which occur in for example, the Kutch earthquake here, 1819 run of Kutch, or 26 January 2001 earthquake here, in Kutch, run of Kutch. Somewhere here you see a small dark red, a little bit faint dark. That's the Jabalpur earthquake. So we are sitting somewhere close to this place. If again in the context of plate tectonics, again in the context of elastic rebound theory, if I take a cross section here and try to see what happens at depth along the arc, that's how it looks like. So you have Indian plate which is subducting, or which is under thrusting beneath the Himalayan wedge here, and which the two plates or the Himalayan wedge is separated from the Indian plate by a fault which is known as main Himalayan thrust. There are a lot of names for it, or you can simply call it as detachment or decollement, and that's where all these big earthquakes are. So that's what we know about. So that's what we know about these plate boundary. We know that yes, during the strain accumulation on this detachment or on this decollement, the strain accumulates in the interseismic period, and then it gets released. And that's how earthquake cycle takes place. And it's the same earthquake cycle which causes deformation. It is the same deformation which causes the topography. So the moment you see a topography, the moment you see mountains, the moment you see beautiful structures, folds and faults, it should remind you that this region is either experiencing earthquake cycle right now, or it has undergone through that process. So there could be some regions where the strain accumulation is very low, or which are dormant, or which are now inactive. But in geological period, this region has undergone through earthquake cycle of deformation, earthquake cycle of strain accumulation, earthquake cycle of strain release, and that's how this topography has been built. So these are the message which I want to give, that when you look at topography, when you look at mountains, when you look at structures, the first thing which should come to your mind is earthquake cycle, the process of strain accumulation, the process of strain release. In the plate bound region, we know that the earthquake occurrence process is sort of simple. We understand it. So there are two plates, and these two plates are separated by a fault which separates these two plates. That's what we call a plate bound region. That's what, for example, Himalayan region. But then in the plate interior region, you can have within a plate, you can have a fault, for example, Narmada zone failed rift region, which does not cut across the entire lithosphere. So the fault is confined within the crust, but nevertheless, it keeps experiencing earthquake. It is not a plate bound region. So that's one category of earthquake occurrence in plate interior region. Another category of earthquake occurrence in plate interior region is that you could have an isolated region where the fault is limited in its extent in terms of depth and in terms of its spatial extent, and earthquake occur only in a small region. For example, the Koyna-Wana region in Maharashtra. So it's only a small region which keeps experiencing earthquake. If you go beyond it, you don't see them. You don't see the deformation. You don't see the. You can have surprises. So you can have a region which has absolutely no geomorphic expression. For example, the Kilari-Latur earthquake. Now, if you, of course, there are claims that there's some Gurudwari rift which caused this Latur earthquake. But if you look at the region, if you go into the region, you see that there's hardly any geomorphic expression on the surface, and those are called random distribution. These are again intraplate earthquakes. So these are interplate earthquakes, and these all three categories are intraplate earthquakes. If you want to give an example for each of them, then this is how it is. So you have Himalayan, which is the where you have plate boundary zones, where you have interplate earthquakes, and then you have regions like Narmada zone failure rift, where earthquakes keep occurring, but it's not a plate boundary region. You have Koyna region where you have localized weak zone. The moment you're out of it, you don't see them. And then you have random distribution, where you have earthquakes like Latur or Kilari. So these are the categories of intraplate earthquake, and I like to give example for each of them. So let's just spend 1 or 2 slides for interplate earthquake, for example, the Himalayan region. And I have already discussed this, that if you take a cross section, you can clearly see that there's a fault here which we call as main Himalayan thrust, detachment, decollement, soul thrust, whatever you can call, and that's where the big earthquakes occur. So it is this fault which accumulates strain during the intersection period, during the period of strain accumulation, and when it exceeds, as per elastic rebound theory, when it exceeds the strength of the rocks, the strain is released in terms of earthquakes. By the way, you can extend the same concept in case of intraplate earthquakes also. The only difference is here the faults are of lithospheric scale. The fault cut across the entire lithosphere, whereas in the intraplate region, these faults are of either they're confined at shallow depth, or at the most they extend up to crustal level, up to crust. They don't cut across the entire lithosphere. So that's the major difference, and that makes these intraplate earthquake as more complex. But then we have the basic difference between these two region or between these two faults. So this is a plate bound region, and this is a plate interior region. I keep calling this, for example, the Narmada zone failure region. Now the basic difference between the two is that since these are two different plates moving with different speed, now if you have some measurements of plate movement or the displacement field measurement here, you can clearly see that so you remember the elastic rebound theory? So you see that the two sides here, one side here and one side here, they're moving at different speed, and then this region here in between gets strained. So you can clearly see an offset in the plate motion on either side of the fault. But when you come to plate interior region, that's the major difference. You don't see them. If you have some method of plate movement here and here, now if you look at this curve here, they're at the same level. So the moment you are out of this region, the moment you are out of this intraplate region, you don't see the deformation. You don't see the process of earthquake occurrence because there is no relative motion between the two. The motion between the two is there are no two different plates. The plate is single plate, and it's only the local fault which is of crustal scale, or it could be at shallow level, which is basically which does not cut across the entire lithosphere, and because of which the deformation or the process of earthquake occurrence becomes totally different. And that's the beauty of these plate interior region, and that's what makes these plate interior region more complex. So that's why understanding of earthquakes in plate interior region is much more difficult, much more complex than the plate boundary region earthquake. Because for plate boundary region earthquakes, we have a hypothesis, we have a theory which is known as elastic rebound theory, which tells us that strain accumulates because of the plate motion on either side of the fault. Whereas in this case, the plate is single. The plate is deforming internally, and that's the major difference between plate bound region and the plate interior region. Okay, now how do I measure this plate motion? I keep saying that if you have a method to measure the plate motion, I use a simple GPS, which is there in your mobile phone, or we have sophisticated instruments also, which measure the coordinate of a point in terms of latitude, longitude, and height. Now, the kind of GPS which I use is very precise. It can give me a latitude, longitude. By the way, these are how do you define a point? You define a point by a unique method, which is in which we have divided entire Earth surface in terms of latitude and longitude. So each point has got its unique identification, right? So if you have a GPS which is very precise, it can locate the point at an accuracy of millimeter level. Then what you do is you take your GPS, measure its latitude, longitude, and height, and then you go again, measure it some other time. You keep doing it again and again until you get a good time series, and then you fit a line into it. So you get the velocity. So that's how you measure the velocity or the velocity or the site motion or the plate motion of a site. So you put a GPS on a site and you try to estimate how it is moving as per the plate tectonics. A typical GPS time series will look something like this. So this is the north, which is the latitudinal position, this is the longitudinal position, and this is the height. So it tells me that this is how this site in Himalaya, for example, these are two sites in Himalaya. That's how they're moving. So its site is moving at this rate in the north direction, in the east direction, and the up direction. That's how that's the simplest method of estimating the plate motion or the site motion of a site. And that's what we do. So we try to estimate that site motion. We try to see whether this site motion or the motion of that site is consistent with what we expect from plate motion. And if the two match, if the site motion and plate motion are similar, we say that well, there's hardly any strain accumulation taking place here. No, I'll not go into that detail, but that's how GPS works. That's how these models work. I'm sorry, it somehow it came back. So what I'll do now is, with all this background, I'll try to give you some examples. I don't have an example of Narmada Son failed drift region for the simple reason because we don't have a lot of GPS measurements across it, but we know that this region has experienced a lot of earthquakes. I mean, there was an earthquake in Bharuch, there was an earthquake which was 1970, 97, Jabalpur earthquake, 38, and there was an earthquake in 1938. Okay, let's forget it. So this region has experienced a lot of earthquakes, but then since we have good measurements across Kutch Rift, which is not different from Narmada Son Rift, the only difference is that probably Kutch Rift is more productive in terms of earthquake. So if you fortunately we have a lot of instrumentation across Kutch Rift because there was a big earthquake which occurred in 2001. And what we have done is we have put a lot of GPS across it. And if you look at the motion at these sites, you clearly see that if you see clearly, if you watch them carefully, you see all the sites here. The motion is towards south, and all the sites here, the motion is towards north. And this is a scale. So it's not a huge motion which I'm talking about. It's a motion of 1 to 2 millimeter per year, but that's enough to cause strain accumulation. That's enough to cause earthquake in this region. Now, unfortunately, we still do not know we know that there's a deformation which is going on, but we do not know what is the process responsible for this deformation. There are a lot of hypotheses or theories that, well, since this region has gone through the episodes of failed rift, so there are a lot of fluids available here. There's a lot of high density material which is available here. There are a lot of weak zones, weak faults which are available here, because of which we have strain accumulation. But we still do not know the exact process. Well, actually, the process can vary from place to place. So the process which causes strain accumulation in Kutch Rift may not be the same the process which we see in Jabalpur or the process which we see in Bharuch region. That's the diversity we live with. And as I told you that the process of earthquake occurrence is much more complex in the plate interior region as compared to plate boundary region. I give you another example here. I'm giving you these examples because these are most common nowadays because a lot of people keep talking about it. So there are a lot of earthquakes which are occurring in Delhi region, and there's a structure here which we call as Delhi Aravalli Fold Belt. This is somewhere here is Mount Abu, Mount Abu region. This is Delhi, and there are a lot of small earthquakes which keep occurring here. Well, again, this region has undergone through episodes of rifting, stretching, sedimentation, and then of course collision between the two cratons, Marwar craton on this side and Bundelkhand craton on this side, and because of which this region is active even now. But if you look at the history of this region has not produced a big earthquake in past. There are a lot of earthquakes which have occurred in Himalayan region which have influenced or caused damage in Delhi region, but all those earthquakes have occurred in the neighboring Himalayan arc region. But nevertheless, this region has produced a lot of small earthquakes here. And these are typical intraplate earthquakes. These are not interplate earthquakes. So, and if I don't want to go into details of the structures here, but believe me, there have been several episodes of clustered earthquake in this region, and to our knowledge, to our understanding, and to the data available, none of them have led to a big earthquake in past 50 years. So assuming that the high seismicity in the region can cause a big earthquake is not certain. So it's not a good idea to say that because there are a lot of earthquakes occurring in Delhi region and hence big earthquake is expected. It's very unlikely because we don't have any evidence of that kind so far. I also give you example of Koinawana region. So there is this region which is hardly 30 by 40 kilometers square region, and so this is Koina Reservoir, this is Wana Reservoir. By the way, I keep saying that people keep saying that earthquakes are triggered by the reservoirs. That's true. That yes, earthquakes are triggered by the reservoir, but the contribution of the triggering could be 10%, 1%. What causes these earthquakes? What causes these typical intraplate earthquakes, stable continuity earthquake, is still unknown. We do not understand it. We try to quantify the strain, that what is the strain which is building up here, and it comes out to be less than 1 millimeter per year across these faults. But what caused this strain? What caused this generation of strain? What is the geological process? What is this structure, this position which causes this strain generation is still unknown. So that's the complexity we live with in such intraplate region. I'll not go into the complexity of explaining how the reservoir interact with the ambient stress or with the tectonic stress. There's another example which you might have heard quite a lot, which is Palghar earthquake. So there's a region called very close to Mumbai, almost like 70 kilometers from north of Mumbai. There's a region called Palghar. So there's a lot of earthquakes keep occurring there. And all the earthquakes are, fortunately, they are very small magnitude, and they're confined in a region of 10 by 5 kilometers square region. There are thousands of earthquakes which have occurred here, and all of them are very shallow, and fortunately they have good correlation with rainfall. All these earthquakes they involve normal motion, and considering normal motion in a compressive Indian plate scenario, Indian plate stable continental region is very difficult. So you don't expect normal earthquake to occur in this region. So that means it suggests that these earthquakes are basically they're not of tectonic origin. They're all occur because of some fluid migration at shallow depth. Fluid migration occurring at shallow depth of 6 kilometers, less than 6 kilometers. So there are a lot of earthquakes which keep occurring in Palghar region. There's another example here, which is again not far from Sagar. This is Amravati. This is close to Amravati district, and there was an episode of earthquake occurrence in this region. This is the blow up of that area, and there were in a very small region of 3 by 3 kilometers square, several small magnitude earthquakes occurred. And when we started looking at those earthquakes, we found that they were all extremely shallow. They were all at a depth of less than 400 meters. So and then when you look at the rainfall, you see that probably all these earthquakes, which were extremely shallow, were all driven by the precipitation. Once the rainfall was over, in that year, earthquake did not happen. Now, somebody may counter argue saying that, well, not every episode of precipitation has caused earthquake in this region. It doesn't happen that way in nature. It's not like the region will produce earthquake in every year. So that's the uniqueness of all these processes.
Sorry for the interruption, sir.
I'm done.
How many more slides you have,
I'm
sir?
done.
Because
I'm done.
next.
I'm done.
Okay, okay, sir.
Thank you. So that's the last slide. That this is what we do with earthquake process. We try to understand them through monitoring. We try to understand how these structures which produce these earthquakes, how they look like at depth, how the strain accumulates at depth, and then we try to understand the seismic hazard of region. And there are a lot of other stuff. For example, there's a lot of effort which is going on forewarning. It's not forewarning of earthquake, but an earthquake has occurred. Now we want to convey this information to the far off side, saying that look, earthquake has occurred. Now the waves will arrive at your place. So that's what called earthquake early warning system. So there's a lot of stuff which there's a lot of research which keeps happening in seismology, and all of it is all summarized here. I'll stop here, but the overall motive here is somehow to mitigate the risk involved in earthquake processes, either through developing building codes, or through developing seismic hazard models, or through understanding the process. So I think I'll stop here because I have already taken too much time. Thank you.